Looks like it's 3 o'clock. Time to get started. I'll go ahead and kick things off for us. On behalf of FCSM and COPAS, I want to welcome everyone to our third of 8 webinars on confidentiality and data access entitled Privacy in the American Community Survey. My name is Paul Schroeder, and I'm the Executive Director of COPAS. Each of these webinars were repurposed from the FCSM conference, initially scheduled for April. Other sessions for the April program have been converted to a virtual FCSM conference taking place on September 21st. And if you have not registered yet, it is actually reopening in the next couple of days, so look out for that. Today's webinar is being recorded, and the video will be posted to the COPAS website within the next week. I now turn it over to Michael Hawes from the Census Bureau, who is the chair of this session. Michael?
Great, thank you, Paul. Can you hear me all right?
Sure can.
Okay, great. Well, good afternoon, everyone. I'm Michael Hawes from the U.S. Census Bureau, and I'd also like to extend my welcome on behalf of the Federal Committee on Statistical Methodology and COPAS to the third webinar in our Privacy and Confidentiality and Data Access series. Today's topic is Privacy and the American Community Survey. As I'm sure most of you already know, the ACS is one of the flagship data products of the U.S. Census Bureau. It would be hard to overstate the importance of the ACS for funding decisions and policymaking at all levels of government, and for research and decision making in both the academic and private sectors as well. When releasing data for the ACS and other censuses and surveys, the U.S. Census Bureau is required by Title 13, Section 9 to protect the confidentiality of the information that we collect from or about our respondents. This is done through the application of statistical techniques to reduce the likelihood that respondents can be identified in our public data releases. Recent advances in computer science and the proliferation of rich external data sources have made protecting those data significantly more difficult. Today's presentations will look at those challenges and we'll explore some of the ways that the Census Bureau and our academic partners are looking to improve those protections for this important survey. I do want to say we'll be having a moderated question and answer discussion after the presentations. So during the presentations, please submit your questions via the chat box, and I'll be compiling them for the discussion. Our first presentation today will be by Rolando Rodriguez, titled A Roadmap for Privacy in the American Community Survey. Rolando is chief of the Disclosure Avoidance Research and Applications Group in the Census Bureau's Center for Enterprise Dissemination. He's implemented methods for protecting respondent information in several censuses and surveys, and is currently involved in efforts to modernize privacy practices in the ACS. His research interests include privacy and confidentiality, missing data, and hierarchical modeling. I'll also say, since last night's torrential storm in DC, my internet has been going in and out. So if I do get disconnected, Rolando has also offered to take over as moderator for me. So thank you, Rolando. And I'll turn things over to you.
Okay, thank you, Michael, for the introduction. And thank you to Paul, Bashla, and everyone else who helped organize this session. I think we all know that the ACS is an important survey, and the privacy of the respondents for that survey deserve to have the protection that they need. And so my talk is going to be about where we're going to go with privacy for the American Community Survey over the next few years. I'll note that any views and opinions in this talk are my own and not necessarily those of the Census Bureau. So with that, first slide, please. So about a year ago, our Deputy Director, Ron Jarman, issued a blog talking about new safeguards for data at the Census Bureau. In that blog, he stated that we don't anticipate the ACS to implement formal privacy or differential privacy until at least 2025. That to mean that the survey won't have any advances in its privacy techniques for those number of years, but that isn't true. We have a large number of techniques that we use to protect respondents in the ACS, and we do plan on reviewing those and strengthening those every year, and we have good reason for that. Next slide, please. So as many of you know, there was a re-identification attack, an ethical re-identification attack done by the Census Bureau on the 2010 census itself. And those numbers made us believe that we have an issue of respondent re-identification in census products. In particular, 45% of the US population had putative links to commercially available databases. Among of those 45% were people, 38%. Just a second for that too. 38% of them had those links confirmed by looking back at the internal census data. And that second number, the 38%, is particularly concerning because that means that if an attacker were to take the links that they could find and assume that they were correct, they would in fact be correct a large percentage of the time. And all of this is particularly concerning when you consider the fact that while census data are supposed to remain, the identities of our respondents are supposed to remain confidential for 72 years, which means for the 2010 census, we have 62 more years of potential vulnerability to increasing data that's available publicly and to increasing computing power. So we had to do something about that, and what we did is that we started to move towards formal privacy methods, most famously now for the 2020 census. Next slide, please. So many people will say, well, surveys have the advantage of being sampled, so there's less disclosure risk for surveys. We don't have such a worry about this issue of re-identification and reconstruction for them. But that's not really true. The high dimensionality of surveys makes the potential for our respondents to be unique within the population much higher. It also increases the number of potential data sets that we can match to externally. And that's important because information shared across all these databases basically makes a key that allows us to re-identify respondents across different surveys and censuses and other data products. In addition, advances in statistical and machine learning models are making it easier to take public data and to try and reconstruct the private data that is held internally by data stewards like the Census Bureau. So we plan to move the ACS towards formal privacy methods, and that has a lot of potential benefits. Next slide, please. Respondents would be able to have a guarantee of privacy that they know the algorithms that we're using to protect them have to meet. Those researchers in the Census Bureau who are working on these techniques can now focus their efforts on algorithmic development and improvement rather than having to make choices about how much privacy our respondents have. That would now become a policy decision and would allow policymakers to be the ones who focus on making that decision and be informed to make that decision. Additionally, data users are going to be able to have much more transparency in terms of seeing the algorithms that the Census Bureau is using to protect its respondents. I think it's fair to say that the amount of transparency surrounding the release of the 2010 demonstration products in terms of the availability of the code and the data is unprecedented in terms of how much external users are able to see about internal processes of privacy. And last but not least, attackers won't have a way of getting around the privacy protections. They'll have to face this wall of noise, and if they want to try to re-identify people, it will have to be through that wall. So there are a lot of good reasons to move towards formal privacy. So why are we talking about having to wait until 2025? Well, next slide, please. So it turns out that common features of surveys, both in terms of processing and in terms of the features that they have, are challenges for formal privacy. Many surveys adjust their weights for things like non-response to certain control totals. All of this can have an increasing effect of how much removing or adding a person to the data set can have, which is an important concept for privacy definitions like differential privacy. Additionally, we have the curse of dimensionality again. High dimensionality makes it harder to design algorithms. One of the first steps from the top-down algorithm that is being developed for the 2020 census is to take the microdata and turn it into a complete cross-tabulation. That's possible with the dimensionality of the census. It is much harder to do with something that has so many cells like the American Community Survey. Last but not least, as we've also seen with the 2010 demonstration products, small populations can be an issue in terms of adding noise. And when you have a survey that both has fewer people in the sample and asks more questions, those kinds of sparsity issues aren't going to get any easier. Next slide, please. So we can't implement formal privacy for the ACS as a whole right now, but that doesn't mean that we can stay still. The risks are out there. The amount of external data is increasing. Computational power is increasing. We have to do something to protect our respondents. So where we would like to go in the future is towards methods that I call here that have composable formal privacy guarantees. That means that they have a definition of privacy that all the algorithms have to meet. Every output that comes from the survey is going to have to go through one of these methods, And additionally, these methods can be added up in terms of the privacy loss they have to a total privacy loss budget that we can communicate to our data users and to our respondents. But what we want to try to move away from are those techniques which I have here labeled as ad hoc privacy, which make a lot of assumptions about which respondents need the most protection and which outputs need the most protection. We want to move away from that. And so there are middle ground options. And one of those is what I have labeled here as non-formal privacy, which are statistical and other methods that affect all of the outputs of the survey in the same way that a formally private method would. Next slide, please. So what do I mean by affecting all methods? Well, if we consider a couple of different types of output that you can have from a survey, for tables, it could mean taking the tables and sending them through some kind of random effects model. For instance, one that considers relationships across time and space. We can then make draws of posterior densities from those models and have a new set of tables that has, in essence, noise injected from being fit through the model. Similarly, for microdata, we can start with microdata that's internal, send it through a sequence of predictive models, and in the end, generate a fully synthetic microdata set that can be used for analysis. Here I've illustrated using classification trees, and we'll have a little bit more information on that in the talk by Dr. Christine Task after me. Next slide, please. So one advantage of moving towards a system where we're trying to use fewer methods of privacy but applied to much more of the data is that simplifying workflows is going to allow for more adaptive workflows. And what I mean by that is that right now we start with an edited ACS file that has, even before weighting has been done, privacy methods applied to it. We then take a file that we have ready for making the tables and for the public use microdata, and then we add even more noise to protect tables. We use different methods to protect the public use microdata, including taking a 1% sample in terms of the population to make the PUMs. That subsampling is for the purposes of protecting privacy. We would like to move towards a system where instead now privacy would be applied only at the very end. So when we want to make our outputs, we have methods for making those outputs have the privacy guarantees we want. And the advantage there is we would be able to develop this file that I'm calling here the internal reference file, or IRF, which will essentially be a file unconfounded by the effects of privacy methods. This can then serve as an internal test bed for various experiments that concern accuracy, how administrative records affect data, how different imputation models for missiness affect data, how weighting adjustments can affect data. We can now assess all of those in this framework without having the confounding effects of privacy. Next slide, please. But we recognize that, well, there's no such thing as a perfect model. So what we're going to do is that we're going to take a page from the Survey of Income and Program Participation and create a validation system that our data users will be able to make use of. What do I mean by validation? Well, right now, when someone takes a public use microdata set from the ACS and does analysis, they take the data, make their analysis, and then they're kind of done. What we'll allow now is that since a synthetic version of an internal reference file will have basically the same format as the internal reference file itself, we can now accept the code that the data user used to make their analysis and send it into what we call a validation server. The validation server will then run their code on the internal reference file and create an analysis from that. We can then use privacy algorithms that are tuned to the specific kind of outputs that the users are asking for to produce a validation result that can be then compared to the original analysis from the public use microdata to help our data users determine how much they should trust the outputs they're seeing from these increased privacy methods. And my colleague, Dr. Jordan Stanley, will talk more about the use of these kinds of methods in the Survey of Income and Program Participation a couple of talks after me. Next slide, please. What this is going into is that data users are going to have an increasing number of ways to access the results from the American Community Survey that they want. All of these outputs here that I've listed, tabulations, a synthetic IRF, the validation results, special tabulations, output from the Federal Statistical Research Data Centers, these can all now use the same base file for their inputs, and then only at the end have tailored privacy methods applied to them that will allow users to get a lot of different potential views of the data that they need for their use cases. And we feel this will be a way of, as we move towards formally private methods, to get data users used to what that kind of system may look like in terms of having different outputs that may, in the end, need to have different budgets assigned to them. Next slide, please. So I wanted to give in this slide an overview of just timeline in terms of where we're going with privacy for the American Community Survey over the next few years. For the synthetic internal research internal reference file and validation server, this year will essentially be development of the synthesizers that we use to make the person and the housing unit level data. Next year will involve review of those files and an increasing presence of research onto how we do validations. In 2022, we'll do internal testing of the synthetic data file and the validation system, especially to get a sense for how well the latter is going to scale to the kinds of use cases and the amount of use cases that the American Community Survey has. Then, importantly, in 2023, the plan would be to have a test done by external users of the system to really get a sense for how well this is going to work for American Community Survey data users, and to get a lot of really good feedback in terms of what kind of final corrections and improvements need to be made to make the final product useful for our data user community. And then the hope would be that in 2024 would be when we'd be able to release a first version 1.0 of the synthetic IRF and validation system. The schedule for how we're going to bring formal privacy to the American Community Survey and how we're going to add new disclosure avoidance methods and privacy methods to our table output is ongoing, but you can be rest assured that it's going to take internal research from the Census Bureau that is going to be aided by internal internal expertise that we have been gaining in applying formal privacy to the 2020 census. Outreach to you, the data user community, for getting use cases, for understanding how the kinds of products we want to generate could be useful for you, and collaboration with our partners in academia and in other institutions for developing the theory needed to bring formal privacy to a survey that's as complicated as the American Community Survey. We have right now a call out for applications for a cooperative agreement that is to research methods generally for formal privacy for surveys. Next slide, please. So I'm going to wrap up here by saying that there are a lot of things that one has to consider in making changes to privacy for a survey the size of the ACS. We can think of what are the use cases for the data, how much accuracy do we need for those use cases, how much privacy do we need to give to our respondents, what kinds of other data sources have the same kinds of data that we're trying to release. And I think it's fair to say that all the major stakeholder groups have some kind of interest in all of those topics that we have to consider when we're trying to advance privacy for the ACS. What that means is that communication is going to be major going forward. And we are getting a lot of lessons learned from our colleagues who are creating the disclosure avoidance system for the 2020 census in terms of how you do outreach and how you get people to tell you how they're using the data. Understanding that is going to be very important when you consider just how many more topics are on the ACS compared to the 2020 census. Next slide, please. So I leave you here with some links to various blogs and frequently asked questions concerning the ACS. I also have here my email address. I look forward to hearing any questions you might have not been able to ask here through email if you would like to write me one. So thank you for your time. I look forward to your questions, and I hand it back to Michael.
Great, thank you, Rolando. Our second presentation today will be by Christine Task, who will be discussing an evaluation and tuning insights from the ACS fully synthetic data. Christine Task is a senior computer scientist at Nexus Research Corporation. She is the technical lead on the National Institute of Standards and Technology Data De-Identification Challenges, including the Differential Privacy Synthetic Data Challenge, which was the first national challenge in differential privacy. Dr. Task is the data architect on the Nexus Sensin project, which develops production-grade privacy-preserving software for the U.S. Census Bureau. Her research interests include privacy-preserving synthetic data, noise-resistant data analytics, and social network analysis. I'll turn it over to you.
Okay, thank you. So yeah, we're going to be talking about what we mean specifically as far as synthetic data for the ACS. And this is not formally private. This is what I'm going to call heuristic privacy. Next slide. Okay, so Nexus Research, you probably haven't heard of. It's a small R&D company in the DC area in National Harbor, Maryland. Virtual these days, as we all are. We work for the census. We have also supported the National Institute of Standards and Technology. And what this means is that over the past 2 years, we've thought very carefully about what it means to make a good synthetic data generator, both with formal and with non-formal privacy. So we're going to give you a quick orientation of that, and we're actually going to give you a walkthrough of our system. Next slide. Okay, so here's the outline of the talk, nice and simple. When we talk about synthetic data, and I know sometimes that word gets used to mean data that we've just happens to mean the right template form, but we've just sort of dreamt up. There's no resemblance to the original data in terms of distribution or properties, but that's not what we're doing here. What we're doing here is you take in the ground truth data, you model that data, and we're going to talk a lot about how we model that data. And then from that model, you're able to generate synthetic data with the same distribution. And we're going to talk a lot about how we determine that we're doing that well enough. So next slide. Okay, so you may or may not be familiar with decision trees. In case you're not, you probably are familiar with a flowchart. So a decision tree is essentially a very advanced flowchart, but here's an example of a simple one. This is a way of predicting whether or not you survived the Titanic, depending on your sex, your age, and whether you had siblings. And if you were an adult male, that's the left-hand branch there, you probably didn't survive. If you were a male who was a child, so that's one jump left, and you also one jump right because you're less than 9 years old, and you also didn't have that many siblings, then there was a good chance that you lived. So this is a way of predicting the value of the variable died or survived based on the values of other variables. This is a very simple one. The one that we deal with have hundreds, thousands of leaves. Next slide. We don't build them. They're trained automatically from the data. So, but we do tinker with them. Let's show you how this works though. So decision tree that we just showed you predicts one variable value, predicts the value of C in terms of A and B. So if I know what A and B is for your record, the decision tree lets me make a good guess for what C should be. But I can stack these. Next slide. So once I know what your A, your B, and your C should be, now I can predict your variable D. And next slide. If I know your A, B, and C, and D, now I can predict your E. And this is how we fill out a full record. And again, the trees themselves are all trained on the ground truth data. They're all learning the real relationships between variables A, B, C, D, and E. But then when we go to synthesize them, we synthesize one at a time down the stack. And next slide. Now, in an actual system, things are more complicated than that, because of course they are. So our software has a lot more features than that. We have indicator columns and consistency checks to make sure that we're preserving the survey constraints and structural zeros. We have variable encoding that helps us handle large variables with lots of values like occupation. Tree parameters. Privacy is a concern. It is actually possible, because this is not formal privacy, to have a record survive this whole way, all the way down the tree, all the way down all the sequences of trees, and come out the end just the same way it came in. And we don't like to do that, right? So we have tree parameters to make sure that we're not singling out outliers in the data and preserving them. We have partition synthesis, and then the rest of this you're actually going to get to see in a walkthrough, so I won't tell you about them. We'll demonstrate instead. But next slide. Okay, so on to how well, right? That's the important issue. If we're saying run on the synthetic data instead of the real data, you want to know how good the synthetic data is. So next slide. And I said we were the tech leads on the NIST Synthetic Data Challenge. That's the National Institute of Standards and Technology, their metrology lab. We care a lot about measuring the quality of synthetic data. So something you want to think about when you're making a metric. How much coverage does it provide? So how well does your metric represent the breadth of use cases, all the diverse use cases that might happen for this data? And something else is how discriminative is it? So how good is it at finding points of disparity between the real and the synthetic data? Next slide. So what we use is a more advanced version of something that was actually developed for the challenge. This is the K-marginal evaluation. And what it does is essentially captures the similarity between the two data sets on correlations of K or fewer features. We usually use K equals 3, so you're looking at all correlations of 3 or fewer features. And that's what we're measuring similarity on distribution. The way it works is this. It's a randomized heuristic. And we start out by, we're going to pick 3 features. So if you're not familiar with a marginal is basically, we're just going to pick a subset of features, and we're going to look at how the data looks on just those features. We truncate the rest of the information, we look at just those features. So here's a marginal. We've selected B, E, and G. Next slide. And here we're looking at the distribution of the data across B, E, G in the real data and the synthetic data. Next slide. And here we're taking the difference of those two and summing that up, the absolute value of the difference. So here it's density, it's normalized, so it's a 0.12. Next slide. So that gave us the score for one marginal, but of course it's not good to just compare 3 variables. What we're going to do is uniformly randomly across all of the features, do this over and over and over again. We're not going to do all possible 3 marginals because that's, choose 3 becomes very, very large very fast, but we do about 10% of them. And that means that every feature is included many times, every pair of features is included. Okay, so here we do it many times. We get many of those scores, and next slide. And what we do, we sum up, we average all the differences in order to get a number. And then we use the NIST trick. It was from the challenge, so it made this exciting. It's a human readable score between 0 and 1,000. And we map that onto the score between 0 and 1,000, which, next slide. And here's the important thing. So 1,000 is what you're going to get if the 2 data sets match perfectly. But we want some baseline. How do we know we're doing pretty good? So what we actually do is we take the ground truth data, the real data. We take 2 different partitions of it, and we run them both through. We see how similar they are using this metric. And that gives us a sense of sampling error, right? Because those are 2 different samples of real people, not synthetic people. And if our synthetic people are as close to the real data as the real data is to itself, right? This is when we're saying we're doing pretty good, right? Because now we're essentially as close to the real data as if we were reaching into an alternate universe of real people in that same city, in that same population, and they weren't the people from our universe. They were different people, but it fit the same distribution. So our goal here is 960s, 980s. That's about where sampling error tends to run in the sort of data we are about to start looking at. And then also, I'll mention real quick, there's more advanced options. I won't talk about them because you're going to see them, but one we aren't going to hit this time, we also do weighted densities. So we handle weighted records like you get in ACS. Next slide. This is Illinois. I assume everybody who's attending this talk knows what a PUMA is, but just in case you don't, that is the public use microdata area. These are the things outlined in blue here. They're essentially neighborhoods, populations. You get down to Chicago, they're very small. In the rest of the state, they're very large just because they try to maintain a constant population. This is the geographical area we have on PUMS data, and everything we're showing you is PUMS data. Okay, next slide. Let's try making a synthetic Illinois. All right, so we do that. We throw the Illinois in the system. We're using our default configuration. Off it goes. We get a score of 971. It's actually a pretty good score. Next slide. But we're not done yet. Because what we can actually do with the way we have the evaluator, we can get a separate score for every single PUMA. So let's make sure that we're not just doing 971 total, but we're actually keeping good performance on every single PUMA. Next slide. Next slide. So we're pretty good in there, right? Like it's not too bad. Just smaller areas we're going to do quite as well. But next slide. We're not doing so good up here at the top, right? So we put the worst scoring ones first, and we can see these are down in the 800s. This is not like 970. We're having some problem modeling these PUMAs. Next slide. And it's these PUMAs right here. So let's go see what's up with those PUMAs. Next slide. Okay, these are the PUMAs. And these are all in Chicago. A lot of them in South Chicago. Next slide. That one might look familiar. This is Obama's neighborhood. And so what we're actually seeing here is that the pumas that we're having some difficulty modeling, these are tending to be very diverse pumas with very complex relationships, often between race and income and school and a variety of other features. And they may have sort of rules or distributional properties that hold for them that don't necessarily hold for the rest of the state, or vice versa. Next slide. So we don't want to do poorly on them. The first thing that we're going to do is try synthesizing just them by themselves. So the idea is that we're not doing well on them because they're not as, they're dissimilar from the rest of the state. They're getting overwhelmed by the rest of the state. We're going to model them by themselves, and they won't have that problem. And we see immediately we're doing better. But we're not doing as good as we like. That's still 920. That's still running a bit low. So let's try improving that further. Next slide. Okay, so into the features of the evaluator. Frequent item set. So what this does is allows us to assign blame. I told you that we do our evaluation by looking at all of those marginals. If there is a variable or a pair of variables that we're doing poorly on, it's going to show up frequently in the marginals that score low. So what this tells us is these are the variables or correlations where we're having problems with our modeling. And we see that ancestry, we're not doing too well on. Not doing too well on some others either, but we're going to go do ancestry first. So let's look at that. Next slide. Okay, so we can do that score for every puma. We can do that on any feature. So now this is giving us a score for every value of ancestry. And we see we're not doing well on West Indies, South Asian, North Africa, and so on. And it was at this point that the data modeler, Ashley Simpson, who was working with me on this, so Nexus data modeler on the Simpson project, said this seemed very familiar because she's from Chicago originally. We recruited her out of Chicago, and her family is from the West Indies. And she had a 3-generation household, and she actually remembers the census taker coming to her house and having some difficulty getting all of this information noted correctly because they had the eldest person was of Asian descent. They had Black and 2 race, and often in West Indies families you have Hispanic and non-Hispanic. It's a complicated set of stuff to model, all in one household. And so it may also be a complicated set of stuff to distinguish. In order for the decision tree to capture this right, it needs to have all the information that it could use to correctly generate this value. And it needs to have enough space to do it, right? So next slide. Well, let's go look a little bit further into what's going on here. So we're seeing that one correlation that we're doing poorly on here is race 2p. It's the second race value. Next slide. So we can actually do evaluation on correlations of 2 variables. So this is, again, we're going to get a specific score here for how you're pairing ancestry with race. And it goes on. There's a lot more values than this. It's just an excerpt for fits on the screen. But you see here, now we found a problem, right? The data A count is the real data. The data B count is the synthetic data. The synthetic data doesn't match the real data at all. It's generating all sorts of people where it's not supposed to. So it turns out the reason that's happening, and we wanted to have a nice demo for you guys to see here. This is actually a misconfiguration of model dependencies in the configuration file. So this had a little bit of code in it that was outdated that it shouldn't have, and the effect of that was to prevent the variable race from having access to as much as it should have to be able to synthesize. So let's fix that. Let's fix and update that configuration file. Next slide. Here we have an excerpt of the ancestry race correlation now that the configuration file has been fixed. And here you see we're doing fine, right? Scores in 800s. You'll note it's a little bit lower score where there's only 4 people in the real data, 1 sample. We've made 14, and this is because we are providing privacy, right? So we should not be matching the real numbers exactly. But in the larger numbers, we're keeping pretty close. Things are looking pretty good. And next slide. Our outliers are outliers no longer. They are much more middle of the pack. There's still more work we could do, right? There's going to be other things we can look at, but we are looking much better here. So next slide. We can do better. Next slide. Okay, so you can see we've got place of birth, age, occupation. There's some other stuff we could look at, but I'm going to take a look at relationship real quick here at the end. So this is our frequent item set. We found the relationship is an issue, and next slide. We do what we do, right? We go ahead and look at our score on every single value of relationship. And you can see that we're actually having some difficulty, it looks like, distinguishing between siblings of the householder. So this relationship, if you're not familiar, is relationship to the person who filled out the survey. And we're having some difficulty guessing if people are a roommate of the person who filled out the survey, or a sibling of the person who filled out the survey, or a dorm mate of the person who filled out the survey. Grade quarters is different. So that's interesting, right? Okay, so we're going to look at one more feature we haven't looked at before. So next slide. Let's actually go look at how the tree that's predicting relationship is making its decisions. So this is a summary of that. It's looking at the features that the decision tree uses. So just like the Titanic used sex and siblings and age, we're looking at the features that are used to make decisions for relationship. And we see, okay, the high-ranked ones, and again, this list goes down way far, and I want to point out it's a depth of tree. They expand exponentially. It's got 766 leaves. It's a complicated tree. But we can see at the top that it's putting a lot of weight on age, marriage, school, PUMA. These aren't things necessarily that are going to distinguish between roommates and siblings. Does it actually have enough information to distinguish between those categories? And next slide. So this is where I say that what we have actually just demoed for you is a SendSend flat synthesizer, what we're calling. But the SendSend join synthesizer, which is currently in development, is going to use neural net graph techniques to explicitly model household social networks. So actually capture the, again, as Michael said in my introduction, social network analysis was my doctoral research. I want to make sure that we are maintaining those relationships and the correlations of variables across people in a household as well. And so we'll be explicitly synthesizing those, and we'll be doing the work necessary to catch issues like this. Next slide. Okay, and just like Rolando said, I also would be happy to hear questions from anybody, either in this chat or via email. I've got my email down there, christine.task@nexusresearch.com. And the system that you saw today, so this was the SendSend synthesizer. This is moving its way from research to production. Very much a command line interface there, but it's not going to be that for forever. It's going to have a nice user interface on it. And please reach out if you'd like to know more. Thank you.
Great, thank you, Christine. And just a reminder, if you have questions for any of our presenters, please type them into the chat box and we'll be sure to include them in the discussion. Moving on, our third presentation today will be by Jordan Stanley, who will be speaking on strengthening privacy protections in the American Community Survey, lessons from the Survey of Income and Program Participation Synthetic Beta. Jordan Stanley is an economist with the U.S. Census Bureau, where he has been employed for the last 4 years. He received his PhD in economics from Syracuse University in 2016, and his research interests include labor economics, health economics, and environmental economics. Take it away, Jordan.
Great. Thank you, Michael. Thanks, everyone, for calling in. This is joint work with my colleague, Joanna Motro, and where Rolando provided a roadmap for the ACS privacy protections, and Christine talked about the ACS synthesizer, I'm going to be focusing on the potential validation system, framing that discussion around our experience with the SIP synthetic beta validation system. Any views expressed here are mine or Joanna's and not necessarily represent those of the Census Bureau or anybody else. Next slide, please. So as Rolando mentioned, there's a trade-off between privacy and utility. And first off, the U.S. Census Bureau is required by law to protect survey respondents' information and identities. At the same time, surveys have many use cases, and there are benefits to having accurate data. increasing data protections will affect accuracy, and having heightened disclosure risk could also affect if and how people respond to surveys. So important surveys like the American Community Survey need solutions that balance disclosure risk and data accuracy. Next slide, please. One potential solution is to have synthetic data. As Christine discussed, the micro-level data set that gets released is modeled on confidential data. The values in the microdata set that's released have changed, but the underlying covariate relationships can be maintained. When comparing statistics based on synthetic data to those derived from the actual data, the underlying data, the accuracy could differ, and a validation system can help to address such accuracy concerns. And we have past experience with such a validation system with the SIP synthetic data that could inform the development of a similar validation system for the ACS. Next slide, please. The SSB validation system starts with an internal data set that we call the SIP gold standard file, or GSF. This takes panels of the survey of income and program participation and links them to administrative records from the Social Security Administration as well as the Internal Revenue Service. And the GSF serves as the input file for modeling the SSB. The SSB is available for public use, and our data users can request validations on the internal gold standard file. And we view this as a successful setup in that validated output has been used in peer-reviewed publications without the researchers actually having ever seen or worked with the internal data. Next slide, please. I'll start by emphasizing that all the details I'm going to go through apply to the SIP synthetic data and the gold standard file and are different from what Christine talked about with the ACS synthesizer. They're different data sets, different methodologies, essentially different setups for the validation system. But for the SSB, we use regression modeling to produce multiple fully synthetic files. In our current version, version 7, we have 4 synthetic files that are created from a snapshot of the gold standard file. This is just a subset of the internal file that only includes the variables we release as part of the SSB. Approved SSB users can run their analysis on these 4 synthetic files, and while validations on the GSF snapshot are recommended, they are not required. So for the SSB, not all of our users are asking for validation. Those that do, their results undergo a thorough disclosure review before we release them to the users. We see this as a mutually beneficial arrangement. The external users get the output they want, and we, along with not having external users working with the internal files, we also get feedback on our synthetic model. And while the validation system helps to address accuracy concerns, the accuracy of the synthetic data is still important. For some users, it's their end product, and for others, it can shape how they structure their research projects or in terms of what they ask us to do validation on. Next slide, please. An undertaking of Joanne and I's work is to compare output from the SSB to the validated output based on the gold standard file. And in the present study, we're quantitatively comparing these estimates by using as data points estimates from previously disclosed research projects from actual SSB users. So we're taking the synthetic results that these SSB users generated and then comparing them to the corresponding estimates from the validation. Next slide, please. So the first figure here is looking at descriptive statistics, so means, medians, other percentiles. The y-axis is the estimate from the SIP synthetic data, and the x-axis is the corresponding estimate from the gold standard file. To make the graph fit on the screen, I normalized estimates to be between 0 and 1. For example, if the average age in the GSF was 41 and the average age in the SSB was 40, the point coordinates, I'd divide those two numbers by 100, and it would be 0.41 and 0.4. So the proportion is still maintained. And the solid black line here and in the next figure represents the 45-degree line, and the linear fit is the dotted red line. you can see that for the cases we were able to study, the correlation between the two is quite strong. It's almost exactly on the 45-degree line, which we view as an encouraging finding. Next slide, please. We can also look at regression output. So these are coefficient estimates. The figure follows the same logic as the previous one. The solid black line's the 45-degree line, and you can see our linear fit is still a positive trend, positive slope, but it's not as strong of a relationship as we saw with the descriptive statistics. This makes sense because the regression models are generally more complicated than simple means and percentiles. Next slide, please. Since researchers often care about far more than just what the value of their coefficient is, we can do some further analysis. So these are comparing 95% confidence intervals. The top number, the first row, is the percentage of cases we looked at where the estimate generated from the SSD. Can we go back 2 slides potentially? And then up. I think I would want to be on, if possible, slide number 9. All right, great, thank you. So that first number there is whether the proportion of times in the cases we looked at where the estimate from the SSB fell within the confidence interval from the corresponding gold standard file estimate. And that's occurring about 18% of the time in the cases we looked at. Thinking about it from the researcher perspective of having their estimate generated from the synthetic data, getting a confidence interval for that, and how frequently the internal coefficient estimate, the one generated from the gold standard file, falls in the synthetic confidence interval, that's happening about 26% of the time. So these numbers aren't super strong, but in many cases with regression analysis, the researcher is most concerned about what the direction of the effect is and whether that effect differs statistically from 0. So we can do more checks based on those ideas. Next slide, please. Okay, so first let's look at t-statistics. So I've cut everything off at 5 and -5, and I've divided the figure. The orange lines represent where the estimate is statistically significant at the 5% level. And I've highlighted here what I view to be good matches in green. So in the middle region there, both estimates are statistically insignificant. So we're getting the same general statistical conclusion from both the analysis on the synthetic data and the analysis on the gold standard file. Bottom left, both coefficient estimates are negative and statistically significant. Upper right, both estimates are positive and statistically significant. The regions I've highlighted in gray are what I would call bad matches, where we have both estimates are statistically significant, but one is a negative effect and one is estimated to be a positive effect. So opposite statistical conclusions would be drawn comparing the synthetic analysis to the internal analysis. Thankfully, for our purposes of assessing how our model is doing, most of the points fall in the green diagonal, and we have just a few points in those gray regions. Next slide, please. Going more into the numbers on this, these are the interaction of sign and statistical significance. So the cases where we have both the same sign of the coefficient estimate and the same statistical significance, in the cases we looked at, that's happening about 69% of the time, which if 70 is a passing grade, we're pretty close just looking at that category. For the remaining categories, we have the instances where there's different significance, and then we've got most of the remainder comes from this different sign, same significance category. And how concerning the number of cases in this group are depends on whether both estimates are statistically insignificant or if both are statistically significant with the opposite sign. So we can look more into these incongruent statistical conclusions. Next slide, please. So here are the counts for, I've broken out false positives where we have a synthetic coefficient estimate being statistically significant, a false negative where the coefficient estimate is significant in the internal but not in the synthetic, and those cases I talked about earlier where both estimates are statistically significant but we're getting opposite signs. And as you can see, both looking at subset and looking at a percentage of the total, the majority of the time we're getting congruent statistical conclusions, whether we're working with the synthetic data or working with the internal data. So we view around this 93% hit rate, if you will, we view this as very encouraging for thinking about a synthetic data set with a validation system. Next slide, please. Looking at broader lessons learned from our experience with the synthetic data, the big takeaway for us is that researcher relations are key. I mentioned before the mutually beneficial arrangement between us and the researchers. Email communication is very important. The researchers help us if there are issues with their code. Researchers have found errors in the data set, whether it be labeling or weird looking outliers. And the system requires a lot of communication, especially for first-time users. There's a steep learning curve, both in terms of working with these data and especially not being able to see the internal data, and also from the disclosure rules and limitations that we have at the Census Bureau. We found there to be a high value in being as upfront as possible with the users about what the disclosure requirements are, providing them with templates for their code, of that nature. And the final note for now is that we have seen synthetic output can influence researcher requests. So it is still important to have accurate synthetic data. Next slide, please. Some considerations thinking about extrapolating this or a similar system to the synthetic ACS. Our primary consideration is labor and time constraints. So with the SSB, we as a branch of 5 or 6 people were able to handle nearly every aspect of the operation manually. So we process the applications, we work with the researchers, we do the validations, and we do the disclosure reviews. Presumably, the synthetic ACS would be a much larger operation eventually, and manual validation may not be feasible, and we may need to have some automation involved. Related to that, there is a need, thinking about a validation system such as this, to have clear established disclosure rules for users to follow. From the very beginning, providing perhaps a handbook or some sort of template for researchers to follow so that they're running all the disclosure statistics we require, understanding the limits, the volume of output, types of output, et cetera. Another consideration is how to best implement disclosure review. We've handled this manually with the SSB, and while some aspects of disclosure review could be automated, others do require manual review. And thinking about the development and testing of such a system, we have some examples of potential ways to reduce disclosure risk in the intermediate period. One would be to limit the amount or types of validation output. Some types of output are riskier than others. Maybe we start out by limiting what types of output can be requested for validations. Based on the quantitative analysis we did with the SSB results, it's encouraging to think about science statistical significance being a sufficient purpose of the validation system, and limiting validations to those types of requests can reduce the workload and reduce disclosure risk. And finally, injecting statistical noise into output would be another potential way to reduce disclosure risk, at least in the intermediate period. Next slide, please. Okay, so to wrap up, some general conclusions. One is that synthetic data with a validation system can help address both data privacy and data utility concerns. The synthetic data helps with data privacy, protecting privacy, and the validation system can help address concerns about data accuracy and data usefulness. In our experience with the synthetic data, we've found that this arrangement works quite well, at least for this data product, and quantitatively analyzing the estimates based on synthetic data to those based on internal, we see a high degree of overlap between the statistical conclusions comparing these two, which is encouraging for future applications. And thinking about the synthetic ACS, we believe that applying a similar validation system is plausible, but the ACS does present several unique challenges that would need to be thought over and tested out along the way. So that is it for me. Thank you all for listening, and I will turn it back over to Michael.
Great, thank you, Jordan. Again, a reminder, if you have questions for any of our speakers, please type them into the chat box. Our last presentation today will be challenges with differential privacy for complex multi-stage surveys. And that will be done by 4 different speakers. Chris Clifton is a professor of computer science at Purdue University. He works on data privacy, particularly with respect to analysis of private data. From 2013 to 2015, Dr. Clifton served as program director at the National Science Foundation. And prior to joining Purdue in 2001, he was a principal scientist in the Information Technology Division at the MITRE Corporation. Before joining MITRE in 1995, he was an assistant professor of computer science at Northwestern University. He is an IEEE fellow and ACM distinguished member. Keith Merrill is an associate professor of mathematics at Brandeis University, studying the mathematical challenges presented by privacy-preserving data publishing. Eric Hansen is a PhD candidate in mathematics at Brandeis University, working under the supervision of Kiyoshi Igusa. His research utilizes techniques from topology, group theory, and combinatorics to study the representation theory of associative algebras. He's also interested in differential privacy and its interplay with data weighting and editing techniques. And lastly, Sean Merrill is a graduate student in computer science at Purdue University under Professor Chris Clifton. His work focuses on privacy and data publishing, particularly applications of differential privacy. Take it away, Chris. Chris, I think you might be muted.
I'm showing
you
he's
are.
unmuted. Are you able to hear me? Michael?
Yes, we can. Yes, we can.
So first, just want to say that while this work is supported by the U.S. Census Bureau, the views and opinions expressed are those of the authors and not the Census Bureau. Next slide. So one of the key issues in differential privacy is determining sensitivity. Differential privacy is calibrated based on the maximum impact that changing one individual could have on your outcome of your query, on your result. And so for an example, if it's a count, how many high-income individuals are on this webinar? Well, changing one person is going to change that number by at most 1. And so we need to add enough noise that, plus or minus 1 isn't that apparent. If we were to take instead, a mean income, well, now we need to look at the maximum income divided by the number of individuals. And so if it's a small room, you need to add potentially quite a bit of noise. If there's a lot of people here, there would be less. And the key is it needs to be not just this particular room, but the maximum possible income kind of divided by the minimum possible number of individuals. Now, we'll get into there. It turns out there's ways you can satisfy differential privacy that are a bit better than that, and we'll get into that later. But this is a key issue, is determining what these values are, and sometimes they turn out to be quite high. Next slide. So, it's even harder in practice because you may have dependence between individuals. For example, how many children are in single-parent households? Well, it's a count, but if you change the parent, then the number of children in that count is changed. If it goes from a single-parent household to a multiple parent household, you've just decreased the number by the number of children in that household, not by one. There's also problems with invariance. Noisy data may not match known values, and this can cause problems. Missing data. There are various techniques that are used to satisfy missing data, and that's what we're going to talk about specifically today, is how this can be a big problem and what we can do to solve it. Next slide. So if we look at this slide, if we fill in missing data through what's called assignment, basically you copy the data from a donor individual who is similar. We can see that those unknown individuals, their color, if we just copy from someone close, we get, you know, 1 or 2 more blue and 2 or 3 more gold, depending on which is closest of that center white circle. But the problem now is if we change one of those gold values to a blue value, it changes not just one, but it changes the corresponding white that we're allocating from that value. It's not just the change to the individual, but it's the missing data that is impacted by them. This increases the sensitivity and requires us to add more noise. Next slide. Where this really gets to be a problem is if we look at the worst case. Well, look what happens here. Right now we have 1 blue individual, 1 gold individual, and if we use the nearest individual to fill in all of those white circles, well, you know, we might end up with one of them being blue, but all the rest are gold. But now if we were to remove that gold individual, all those gold turn to be blue. The count of gold versus the count of blue has just changed by the entire count of missing data items. And, you know, this causes us to add way more noise than we can really handle. Now, I'm going to turn it over to Keith now to talk about some of the solutions. Next slide.
Thank you, Chris. As Chris just said, my name is Keith. So how are we going to solve this problem? Well, as Chris pointed out on the previous slide, what's really going on here is that the sensitivity is being increased because the same individuals are being used as donors for numerous missing values from various missing data tuples. And so an obvious idea and a very natural idea, and one that has been historically widely used, is to simply limit or remove the possibility of a single individual being used multiple times. A great example of this is hot deck imputation, which serves to limit how often someone can appear. An extreme example of this would be where you simply don't reuse any donors at all, and everyone can only impute on at most 1 individual. So the great question is, does this reduce sensitivity? Is this tried and true method well suited to formal privacy? And the answer, unfortunately, is in that naive sense, no. And so what we have here is a sort of toy example. Imagine that the yellow and blue circles have values that are filled in for some query that you're interested in, and the squares and diamonds below them do not. And color is being imputed from the line directly above it. It does not matter, by the way, whether the yellow circles or the gold circles and the blue circles represent exactly 2 individuals who are being used a lot, or just happen to be different individuals, but they have the same answer to this query that you're interested in. Notice that right now, we would have 4 gold squares. That is, all 4 gold circles would be imputing their color on the squares below them. But if we were to delete that first gold circle, everything would slide over 1. The count would suddenly drop to 4. This is unquestionably a silly toy example. The problem is that naive formal privacy methods, naive differential privacy methods in particular, have to take these kinds of toy examples into consideration because they have to cover all the possible scenarios. So we're going to talk a little bit about ways that we can still do that, but without having it impact quite this much. Next slide, please. So what would be some putative solutions to this problem? Well, you could simply ignore missing data. This would completely remove the need for imputation. Now everyone's sensitivity goes right back to 1 again. And from a formal privacy standpoint, this is a great idea. The problem is that for many of the queries that people are interested in, that users are interested in, this would heavily bias results. That is because the data that's missing is almost never missing completely at random. And so as we're going to see concretely in the evaluation slides, you could do this. The variance is 0 because everything, there's no randomness to this mechanism. The sensitivity would be 1, but the biased results make this impractical for use in this case. So we're going to come up with some lower sensitivity methods. That's what we're really after. And a key one here is smooth sensitivity. Next slide, please. So I don't need to belabor the details of smooth sensitivity in particular. I promise I will not read through that formula at the bottom. That formula is just there to give you an idea that there is some real math going on behind this, which bolsters and supports this. Also, because if people are looking at the slides later and are interested, this is the formula that appears in this smooth sensitivity paper, which was published in 2007. But the key takeaway from smooth sensitivity is that, yes, these toy examples exist, but they're unlikely to be arising in practice, and not just arising, they're unlikely to even be close to what happens in practice when you endow the possible sets of responses with some metric. The pathological data sets are far away, and if we can leverage the fact that they're far away, they still have to be accounted for. You have to account for them, but you can do it without naively requiring as much noise as would be required to protect in that case, because again, you're not in that case. So this is a very clever way of sort of leveraging that those cases need to be accounted for, but that they are unlikely to occur or even close to what would occur in practice. Next slide, please. So our goal then is to come up with a way to do deterministic nearest neighbor imputation on real data sets, but in a way that doesn't require the gratuitous amount of noise that a naive application would. And we want it to be not just better, but we need it to be computable. We need it to be practically computable. And so that's for a wide variety of queries that people are actually interested in, particularly means and counts, a few others. That's exactly what we've done. Next slide, please. So I'm going to leave you in the capable hands of Eric Hansen now to go through some of, but very lightly, the technical details of what exactly we've done.
Thank you, Keith and Chris. Yeah, so I get to tell you all the technical details. So there's a lot on this slide, I know, but I'm going to kind of walk you through the key takeaway of each of these bullet points. So this quantity that we end up studying is this thing called L1 of D. And the idea is if we take a data set D, you can think of this as being the real data set or the real sample if you want to, and we make a change. We either add somebody or delete somebody. This is the largest possible number of people who can have their donor change when we move between those data sets. So in order to utilize smooth sensitivity, what we need to understand is if we take two data sets, is the distance between them increases, the distance being the number of tuples on which they differ, how fast does this quantity L1 of D grow? And the answer is that the growth is bounded linearly. This formula here below the second bullet point, it's a linear function of the distance. So what this says in words is that if a single individual is eventually going to be a big donor, donate to a lot of tuples, they're probably already doing that now in the current or real data set if you prefer. Next slide, please. So the idea is that if we remove a donor, the query can change based on how many times that donor appeared in the data set. Whereby appeared, I mean imputed their data to somebody else. How many donees did they have? So we have these two ways to bound these local sensitivities, the amount that we can change going one step from a data set in terms of this quantity L1 of D. So we see the first one, if we take a counting query, it's just L1 of D plus 1. So L1 of D is like the maximum number of people a donor could be imputing on, and then the plus 1 for themselves. And then the second one, if we take a mean query, we take B to be this top coded value of some attribute.
we have to top code it in, we have to top code some value. Otherwise, like let's say we're talking about average income for this group, we could just add a hypothetical individual of as high of income as we want, and we could make the mean jump as high as we want in one single move to the data set. So we have this top coded value, we have the size of our population, and it's just this 1 plus L1 of D multiplied by this ratio B over S. Next slide, please. So this is perhaps the most technical slide, but again, just to give you kind of a hint of what our techniques look like. So we can turn these into smooth upper bounds, and smooth upper bounds come with this parameter beta, and they work for any parameter beta greater than or equal to ln of 2. And proving this follows essentially directly from the original smooth sensitivity paper. Next slide, please. All right, and now these are the mechanisms we can make based on these smooth sensitivities, these smooth upper bounds. And so here we can take any epsilon greater than 0, our privacy parameter, and we have this PDF. It's, X is this PDF. It's called the generalized Cauchy, and we sample from that PDF. We multiply by this 1 plus L1 of D in the counting case, 1 plus L1 of D times B over S in the mean case, and divide by this number ln of 2, and we get an epsilon differentially private mechanism. And each of these has finite variance as long as epsilon is at least 4 times the natural log of 2. So this brings up one of the subtleties with smooth sensitivity, with something like the Laplace mechanism, the more naive implementations of differential privacy. The parameter can get as small as we want without making the variance of the mechanism become infinite. That's not the case here. We actually get infinite variance, or at least infinite theoretical variance, if we choose epsilon to be too small. Next slide, please. So now I'm going to turn it over to Sean Merrill, who's going to talk about how we evaluated these mechanisms empirically.
Yeah, thank you, Eric. I'm Sean Merrill, and I promise there are no more formulas. There will be some pictures though, so don't worry. So there is an inherent trade-off between bias and variance when it comes to error. We needed a test bed where we could evaluate that trade-off because, as was mentioned before, ignoring the values or ignoring imputation and missing values inherently has a lot of bias, but we hope that it has, we hope that we can reduce that bias. So we based it on the 1940 census data, which being a complete count of the country, we gave us a ground truth without having to deal with any of sampling error or weights or anything like that. But unfortunately, that data doesn't have the ability for us to make missing data. So we then learned a model from the ACS data, which has better representation of the relationships of the values so that we could learn a model for the missing data. This allowed us to apply the model on each run of our experiment to generate our realistic looking missing data with which we can apply our mechanism. So next slide, please. So these two pictures are actually the exact same question. We just added the naive implementation of some form of global sensitivity with the Laplace mechanism on the left. As you can see, it's sort of laughable, the amount of noise that it adds. So that's our comedic value of the talk. The red line in both of these is the true value on the data. And then I'm going to focus on the right picture. So the left column that says ignored is the results of if you were to ignore the data or ignore the missing data. What would your answer be? Our right value, or the right column, is our imputation method. As you can see, our results have slightly higher variance, but are significantly closer to the real value and have significantly less bias. Next slide, please. So here we have two more queries just to show that our results seem to be generalizing to multiple different queries. We didn't handpick one of them. But again, you can see that we have significant or slightly higher variance, significantly less bias. Next slide, Chris. You're muted.
Yes. So, yeah, just as want to thank you all for taking a look at this. If you have questions about it, you can ask them now. We already have one question, which I'll let the moderator bring up. I will mention we're pretty easy to find. We're all between our university and name become unique. And so it's easy to identify us and find our email addresses. If you're really interested in this and really want to get into it, I will also mention that Eric and Sean are both in their final year of their PhD programs, and you could look into hiring them if you really want to get the full details on this. So back up to Mike.
Great, thank you. So let's actually start with the question that was posed in the chat, which I think, Keith, you already typed in a response, but for those who may not be following the chat, the question came in, are you also controlling for the number of potential donors when thinking about which donors are potentially big?
And so I'll start on this. This is actually one of the tricky things. As you noticed with smooth sensitivity, we need to look first at the actual number or the most possible donees that someone can have in the current data, and then expand out to look how that would be in adjoining data sets. And so in that sense, it is impacted. And it turns out that one of the difficulties and one of the clever solutions in the approach we are taking is managing exactly that question, because we have to ensure that if you change, if you could potentially have a cell where, like you say, if we use the hot deck approach, we get that problem where it changes all the imputations potentially by changing one individual. And so we needed to have a method that avoided that, and also avoided, and so if you have a lot of donors in the same cell or in the same, that are very similar, in this case, a bunch of identical donors, you need to make sure that changing one individual doesn't suddenly cause you to switch who those donors are matched up to. And we handle this through a carefully worked out and clever assignment. We have a paper that we can send you a copy of that goes into the details on how that's done. But yeah, it's a very good question. And that was one of the particularly challenging problems we needed to deal with in order to make this work.
Great, thanks. Here's a question for Rolando. So you talked about engagement with the data users in the process of modernizing the disclosure avoidance for the ACS. Like, how do you plan on involving data users in that process?
Thanks for the question, Michael. So, I think one of the major lessons that we are getting from our colleagues who are working on the 2020 disclosure avoidance system is that, it is good to have, of course, these broad measures of accuracy, like the ones that Dr. Tass talked about in her presentation. But, there are a lot of use cases even for census data, let alone when you go to the ACS, which has a much larger set of concepts that it covers. And it is vital, like early on, to get the engagement of particularly data users who know of official use cases for the data, who have a lot of experience in using the data for making statistics that are used to make decisions that affect people in the United States. So, I think the plan is, as early as we can, to identify groups of users who would be useful in communicating with, to start getting these sets, not just getting sets of use cases, but identifying pockets potentially of other users who might also have use cases that we might normally not get to or have considered. Our hope, of course, is that we will leverage the expertise of our internal subject matter analysts, subject matter experts, in developing and fine-tuning the generalized metrics that we're using to evaluate synthetic data and the validation system. That's going to be very important, just given, as I said, the wide dimensionality of the data like the ACS. So, there are a lot of discussions going on right now about how best to start this engagement. But I do think, as I said, one of the lessons that we came from 2020 is, bring people in and try to do things like get people access so they can look at things internally. That's definitely something we're going to look at. And then we do plan a public test of this system. So I think a lot of effort is going to go into deciding how we're going to select test users for that and identifying kind of the best way of selecting them to get the most out of these new data products.
Great, thank you, Rolando. I think we have another question for you that came in from Doug. The Census Bureau appears to be pushing a formal privacy solution for the ACS before sufficiently demonstrating a true privacy problem. What direct evidence is available that demonstrates a realistic, operationally viable threat to the ACS? And does the Bureau see any inherent features of the ACS's design that may make it difficult to perform a successful attack?
So, this is almost somewhat of a philosophical question, in that, do you react, or are you reactive? Are you proactive to potential risks and user data? I think given the ability to match on the 2010 census, which has a much smaller set of potential variables to match on than the ACS, I think the feeling, at least my own feeling on this, is that we can't wait for a re-identification, for instance, as an internal attack of re-identification on the ACS to work before we start to make new privacy methods for our respondents. That being said, I do appreciate the value. Well, for instance, the results from the 2010 census in terms of re-identification, I think, were very valuable in moving the discussion forward on how much we need in terms of new protections. I will agree that that would be a useful thing to see for the ACS, but now it becomes a resource question, because doing these kinds of identification attacks and reconstructions takes a lot of work. Do we put that work towards doing making the proof or getting ahead of the problem? And right now, we're trying to get ahead of the problem.
Great, thank you. Here's a general question for any of the panelists who want to comment. One of the major challenges with the application of differential privacy for the 2020 decennial census has been the policy trade-offs that are going to need to be made in allocating privacy loss budget to support different use cases of the data. So allocating your privacy loss budget across different query sets or across different tabulations to support demographic analyses versus redistricting use cases, et cetera. Are there similar policy trade-offs that are going to have to be made for the approaches that you're investigating?
I guess I can take that one. There will certainly be trade-offs that we're going to have to look at in the use of American Community Survey data. That being said, one of the differences that we have here is that with the ACS, there is, of course, a baseline measurement of survey error. And as opposed to the census, where people are kind of used to saying, well, these numbers have no noise, and we're now adding noise to them, and they weren't noisy before. You can't really say that with numbers from the ACS. So I think where the conversation is going to need to be is, how accurate are some of these use cases already if we look at the standard errors? And then how much more noise is getting added on top of that from whatever privacy method that we happen to be using? And it's going to be important to kind of keep that in mind going forward, because it would be, I think, unfortunate to reject new and better privacy methods for adding noise into areas that were actually already too noisy to be actually useful for the use case intended. So there's going to be a lot of differences moving forward between how we're going to assess the ACS for privacy versus the census. But again, there's a lot of useful information that we've gathered from our colleagues in 2020 about what to look for and how to engage people. But yes, I do think in the end, keeping in mind that we're dealing with a survey is going to affect absolutely every stage of the process.
Great. Do any of the other panelists want to weigh in on this question?
So
I will also say one of the things about these formal privacy approaches is we can say how much noise is coming from the privacy protection, and so if you look at the current approaches to most sample-based surveys, for example, the ACS provides confidence intervals and ways to calculate confidence intervals. These are based on the fact that it's a sample, and because of the sample size, you're going to have confidence intervals. As we are developing differentially private methods, we're looking at ways to develop confidence intervals that reflect the total error from not just the sampling error, but also from the disclosure avoidance, so that you have a better understanding than you currently would of, as Rolando pointed out, whether the answers you're getting are really sufficient for your use case.
So work. I work differentially.
Yeah, Christine, I think your audio is cutting out on you there. All right, we are approaching our endpoint here. Do any of the panelists have any last words, any take-home messages they'd like the attendees to hear?
I mean, I think I'd like to just sum up by saying that, the ACS has a benefit of time that we don't have with the 2020 census. And so we very much want to take this at a pace that allows people to feel like they're getting the information they need when they need to get it. So I would encourage all of you to reach out right now to me if you would like, but in the future we'll have other venues for reaching out to the Bureau, and let us know your concerns. We want to hear them. We want to hear how you use the data, what worries you have about using these new data products we've been talking about, worries you have about moving towards formal privacy, and we'll keep that conversation going. And I think if we just all listen to each other and continue to have venues like this in which to talk during these difficult times, we'll be able to get this done in a way that I think, I don't want to say makes everyone happy, but that people feel like they've had the say in the process that they feel they should.
Any other final thoughts? All right. Well, on behalf of FCSM and COPAFs, I'd like to thank our panelists today. I think this was a very informative session. Please stay tuned for the upcoming webinars in this series. I believe the next one is in, actually, Paul, I don't have the schedule in front of me. Do you know when the next one is scheduled?
Yes, it's scheduled for August 13th.
Great. So yeah, please stay tuned for that one. And thank you all for joining us today.